Continue. Okay, so today, chapter 10, we will introduce the concept of angular mass, which we call moment of inertia. And that's the missing piece that then makes all of angular motion and rotational kinematics fit into rotational dynamics and work and energy and everything else that we had from the whole rest of the course that had mass in it. So we started off with kinematics, and then we introduced force. Force equals mass times acceleration. And then we had, everything from work to energy, momentum, all of those concepts have mass in them. And when we go into rotational motion, the weird thing is it does matter how massive something is, how much mass it has, but it also really matters where that mass is located relative to the axis of rotation. And so we call it moment of inertia. The other term we could use is rotational mass, angular mass, something to give the idea that it's not just 4 kilograms, but it's something that also accounts for how that mass is placed around the axis of rotation. So that's the main new concept for today. On Friday, we'll take a step back and I'll say, hey, do you have any questions from the chapters 8 and 9 homework material? Because that will be the basis for the quiz on Friday. That means that the ball is in your court. You have to do the chapter 10 homework, and there's not much of it, but you have to do the chapter 10 homework and take a look at the practice exam so that when we have the real exam a week from Friday on April 30th, you will have a chance to ask any questions. So on Wednesday, April 28th, it's the questions ahead of the exam. Again, I'll be with you for the exam. We'll be here on Zoom together. And if there's a question you don't quite understand or you want a hint or whatever, I'm here on chat to try to point you in the right direction. This process where I'm available to answer questions on chat, I think has served a number of students really well. And some of you are maybe too shy to ask the question or something. Please don't hesitate. Ask questions if you have them, and then just recognize my limits. I am, somewhat slow. So if I get the same kind of question over and over again, I can copy and paste. But if I get a new question, I have to look at the exam, see what, where the confusion lies, and then try to formulate an answer that's a reasonable hint or nudge in the right direction. And I'm not the world's fastest typist. So just give me a little patience there. And if I don't answer your question, maybe it's because it came in a barrage of things all at once and it's disappeared up the chat scroll. So always feel free to give me a poke and say, hey, I asked you about number 4 and I haven't heard anything yet. And I'll get to you with my sincere apologies. So Wednesday, May 5th is the last day of classes. And on that day, I will be here to satisfy any last bit of confusion you have. If you come and say, dang it, I thought I understood the football question, but I got it wrong on the exam way back when. Can we just go over that one more time so that I'll have it down pat for the final? Because I know that you promised me that the football question would be on the final exam. So I definitely want to get that one right because I know it's going to be on there. Or whatever other questions, whatever has been bugging you, I never quite understood this. Can we go over that? That will be the last day of classes, as much as you want to go over things. And then I have no vote in this. The final exam is determined by the registrar's office such that none of you will have, final exams are these 2-hour blocks. And so they're set so that you don't have 2 final exams at the same time, which would be a bummer. So our final exam spot for our class time, Wednesdays and Fridays at 10:50, is Thursday, May 13th at 8 a.m. That is the time. Yeah.
Sorry. Will we know our grades for exam 2 before class on Wednesday, May 5th?
Yes.
Okay.
I say that is my pledge that I will get the exams graded. Part of that ball is in your court because you take the exam and then you have the option to take it a second time and keep your average score. So I will get them graded as soon as I can the first time through. And then balls in your court to do it the second time if you want to, so that you will know what your score is. I can commit to Wednesday morning finishing up any grading that I don't have done yet. So class time, you'll know. I have emailed Professor Logsdon about getting lab scores because those have to be put into your grades as well. And it's always one of those things where lab instructors are trying to be flexible and give you guys time to hand in all your assignments and get everything done. And then they have to grade them. And then they have to send the grades to me to then put in for your grade in the course. So sometimes that gets a little delayed. You probably have a decent idea how you're doing in lab. Just keep that in mind that I don't have those scores yet. So Thursday, May 13th, the final exam. And if Thursday, May 13th at 8 a.m. is when I will be here on Zoom with you while you take the final. If you choose not to take the final, that's fine. If you choose or if you need to take the final, you want to take the final, but you're not going to be around or available or something on May 13th, we can make arrangements for you to do it at another time. But I'm probably not going to be able to commit to being here on Zoom with you while you do it, just because that's how that would work out. Okay. Stop share.
Hey, Professor.
Yeah.
If we feel the need to take exam 2 again, how long of a window do we have to do that?
I will try my best to get exam 2 graded over the weekend. So, by Sunday, Monday morning kind of deal, I'll have the first attempt graded. I hope. Yeah, so I'll see how quickly I can do that. Used to be my one amazing skill is that I was a fast grader. If after exam 2, with quizzes, homework, lab scores, and the other exams, you already have an A in the course, and I'm a little, because Salem State doesn't do A pluses, I feel like I can be a little merciful and have the level for A just be a little bit, start a little bit earlier than some people do. If you have a 92 or higher, you will have an A in the course. And if you already have an A in the course, The final exam can bring your grade up, it can't bring it down. So if you already have an A, you have demonstrated to me that you have a good mastery of the material from exams 1 and 2. Those are the basis set for the final exam. So you've already shown me that you know it. You don't have to take the final exam to prove it again. And so you will have your A. And in truth, if you have a B plus at that point or a C, and that's all you really ever wanted in life, you don't have to take the final, but it's my hope that if you have a C, you would take the final and kick butt on the final. You can really do well on the final exam. It is selected questions from exams 1 and 2, and you can bring your grade up a little bit higher. I would love for you to be able to do that. So why are the 8 and 9 homework answers hidden? I don't know. I'll have to look at that, Corey. I have no idea why that would be the case. I must have set it up wrong. I did, let's move this. So our current front page is, make sure it's showing up. Current front page is finish strong, because I want you to finish strong. But if you scroll down to the bottom, our page for last week, you can click on it. And I have now posted the video lecture from chapter 9. I never got to that last week. I hope you all had a great day last Friday when we did not meet for class. I personally had a good day. I didn't get everything done that I wanted to get done on Friday, but then I did manage to get it done over the weekend. So I call that a victory. Where's the PowerPoint? Here we go. Sorry, looking for stuff. Always a mess. Oh, not that. View. Okay. All right. Are we good? Fairly organized? Happy to answer any questions as you have them. I get a little distracted, but not too bad. Hey, I have absolutely no idea how evaluations are gonna be working, but they're online. Since this is an online class, there's online evaluations of the course. So any of your classes that are online, labs, lectures, everything, there will be an online, what we've been using at Salem State forever is the SIR2, probably stands for something. I'm not sure what it stands for, but it's how you evaluate different aspects of the course. And I know you're going to be bombarded with them, with all the classes you're taking. But please, try to, give meaningful feedback. It helps, helps your professors know, where they're hitting the mark and where they're not, and things change. And certainly the way this class is going on, I hope that you're perceiving it as organized and that there's a plan and that we're working toward that plan. But if you're not perceiving that, it's helpful for me to know so that I can try harder to, communicate the plan as we're moving forward and, whatever the things are. So do take evaluation seriously. There's a lot of weird stuff, but like junior faculty that don't have tenure yet, get evaluated in every course, every single semester. Tenured faculty get evaluated in, certain courses. It's not, every single course. So you may not be bombarded depending on who your faculty are, but evaluations, they're coming. They're just really late and it's very bizarre. Okay, rotational motion and angular momentum. We have talked a little bit about rotational motion so far. We have our equations of kinematics for rotational motion that we've established, and it looks like the regular equations of kinematics with a little bit difference. And then this PowerPoint is a little bit of a mess, so be patient with me as we move forward through it. Ooh. Yeah, this PowerPoint is a PowerPoint that I have sometimes used when I put like chapters 9 and 10 into one single lecture. So I copied some of the slides and put them in here. So I'm going to blaze through some of the slides because we already talked about it, but then we're going to get to the new stuff. You do not have to take the final exam if you are satisfied with your grade when we have the scores for exam 2, quizzes, labs, everything. If you're satisfied with your grade at that point, you do not need to take the final. The final can bring your grade up, it can't bring it down. So if you're happy with where you are, you can stop there. Okay, so rotational motion. This would be moment of inertia. If you've ever watched figure skaters doing their spin moves and they start rotating kind of slowly and then they pull their body in tight and they spin faster and faster. That's actually a conservation of angular momentum, and we will talk about that coming up. So we have something rotating, and we talked about the angle theta being angular distance. And we have this relationship between linear motion, the tangential linear velocity of some point, some distance away from the axis of rotation, and the angular velocity. Angular velocity is radians per second. Linear velocity is meters per second. And so the two are related to each other if we have a set radius, a set distance from the axis of rotation that we're talking about. There's translational motion. I guess this is the dude jumping on the trampoline who doesn't spin around. And then this is a combination of translational and rotational motion if you do a somersault while you're jumping. Translational motion, linear motion, you're driving your car down the street, your car is moving in a straight line. If you look at the tires on the car, they're spinning around and moving forward. It's a combination of translational motion and rotational motion, the tires on your car as they go down the road. So we talked about torque. It is the cause of angular acceleration. Something's not rotating and then it is. So somewhere from not going around in a circle to going around in a circle, we have some form of acceleration, not necessarily linear acceleration, it's rotational acceleration, angular acceleration, and we call that thing torque. And we have the relationships between torque and linear force, and then, and we talked about all this. These are all slides we've seen before. Kind of a mess, I'm sorry. And then we talked about center of gravity briefly. And now we get to the topic for today. Tangential linear force, that's the FT, that's the force that is being directed tangent to the actual path. The actual path is going around in a circle, but the tangent is the linear right here, or it'd be linear right here, or linear here. The tangent is perpendicular to the rotation thing. Parallel? Parallel. So tangential linear force equals mass times tangential linear acceleration. So when we talked about tangential linear velocity being r omega, we also have tangential linear acceleration is r alpha. Alpha is the angular acceleration, radians per second squared. So this is just the definition of translating angular motion into linear motion. And we're able to do that because anytime you have rotational motion, you could imagine that the thing isn't going to rotate, it's going to go in a straight line. And so for that instant, we have a linear force or a linear velocity or a linear acceleration. It's all interrelated. But when we take that definition one step further and say, okay, torque, which is the angular force, is the linear force times the radius, then we wind up following the definitions to say, okay, well, if torque equals mass times acceleration, then all of this information gives us this strange definition of what would be angular mass. Because otherwise the math doesn't work out, but the math, the concepts moving from linear motion into rotational motion, we wind up, if we keep track of r alpha, so Ft equals mass times r alpha, and then torque equals FTR, we wind up with another r, we get mr squared, r times r, mr squared alpha. Mr squared, and I'm sorry that this is going to be a little bit painful and confusing. Mr squared is standing in right now for this thing that we're going to call angular mass, which is moment of inertia. But wait, there's more, because that mr squared only counts for something where all the mass is way out here at the radius. So this one, yeah, this is mr squared, the moment of inertia for the plane flying around attached to a massless string. But let's clear, close, move ahead. It's different for different shaped objects. Now, why they chose to do this weird shape, I have no idea. But the process here, and if you ever took pre-calc or calc or something, this is starting to look a little bit like integration when you're doing a sum over all these tiny little points. But don't fear, I'm just going to give you specific shapes and specific moments of inertia. But essentially what we're doing is saying the net torque, the total torque, is going to be the sum of the moment of inertia times the angular acceleration for every little molecule that makes up any shape, and how those molecules are placed around the axis of rotation. So hold up, because we're getting to a good point in just one moment. Oh, come on. Oh. And so, as you can clearly see on this chart of things that you cannot clearly see, what I will give you on any exam that covers moment of inertia. Truly what I will do is I will include the equation for the moment of inertia for the object in the question I'm asking, but I will also give you a data sheet so you can look it up in a way that you can see it, you know, that it won't be a mystery to you. But here we have something that's a hoop. A hoop is something where all of the mass is at the radius, is at the perimeter, and that's the mr squared. The moment of inertia, the angular mass of this object is the literal mass of the object in kilograms times the radius squared. And so the unit for moment of inertia for angular mass is kilograms times meters squared. There's no new unit that we're coming up with, but just for moment of inertia, that's how the units come out, kilograms times meters squared. So here, this is a solid cylinder or a disc or like a big hockey puck or whatever solid round thing you can think of. If this is of uniform density, then what we would say is the moment of inertia is 1/2 mr squared. And the uniform density matters because the mass will be evenly distributed through the whole object. And then there's all sorts of other permutations, a solid sphere, and then a hollow sphere. So a solid sphere would be like a bowling ball or maybe a baseball or softball, whatever ball you have that's solid packed throughout. I can't even read this, but you know, it's 2/5 mr squared maybe. Versus a hollow sphere, this would be more like a basketball or a tennis ball or something where the mass is all at the edge. There's a formula for that one too. So we will use moment of inertia in some more complex analysis. So I just want to warn you about that. Do I have to do this example right now? I don't think so. Let me get to I don't want to talk about work just yet. I guess we have to. Okay, so set moment of inertia aside. We will get back to it in just a moment. Everything else we did in physics so far, we started with kinematics, then we introduced the concept of mass. The concept of mass led us into the world of forces. Once we had forces, we started talking about work. Work is typically, when we talk about work, we said work is force times displacement, right? So work is F x cosine theta. And so if I, you know, lift something up, I'm doing work. Hold on one second. Fx cosine theta. So work is angular for rotational work is angular force, that's torque, times rotational distance, that's theta. We don't have to worry so much about the angle because it's constantly changing. So this is rotational work. It's the same units as it was for linear work in joules. Kinetic energy was 1/2 mv squared. Well, rotational mass is moment of inertia. Rotational velocity is omega. So it's 1/2 I omega squared for rotational, annotate, clear all drawings. Rotational kinetic energy, 1/2 I omega squared. And it will matter what the shape of the object is for how much, for what value we plug in for I. So solid disk would be I equals 1/2 mr squared. And so it'd be 1/2 times 1/2 mr squared if we're doing the kinetic energy of a solid disk versus the hollow cylinder disk with all the mass on the edges. That one was I equals mr squared. It makes a difference how the mass is distributed around the axis of rotation. And we will look at examples from the practice exam before we finish up on this. Sorry. So rotational kinetic energy, 1/2 I omega squared. The unit is joules. Gravitational potential energy is what it always has been, mgh. So it'd just be gravitational potential energy at the top turns into both linear kinetic energy and rotational kinetic energy. So gravitational potential energy will turn into rotational kinetic energy, which is 1/2 I omega squared. But if the two cylinders here have the same mass, they would have the same gravitational potential energy at the top of the ramp. But as they roll down, some of that potential energy turns into linear kinetic energy. That's how fast it's rolling. And some of it turns into rotational kinetic energy. And there's a difference in how the mass is located. So the solid cylinder, the difference, angular mass, this one is 1/2 mr squared versus the hollow cylinder is mr squared. So the solid cylinder has half of the rotational mass. Therefore, it has more energy left over to go into linear kinetic energy. And so this is an example that I typically do in the lecture hall. I roll these two things down a ramp and it's not even close. They have exactly the same mass, actual mass, to begin with, or always. They have the same actual mass, but the race rolling them down the hill, converting the same amount of gravitational potential energy into kinetic energy, the solid cylinder wins by a considerable distance. The math for this involves conservation of energy. Conservation of energy means at the bottom, the final linear kinetic energy, rotational kinetic energy, and final gravitational potential energy, we call that 0 at the bottom of the ramp, equals whatever the initial linear kinetic, rotational kinetic, and gravitational potential. This would be high at the top. So when you do the math, you wind up with, it's not rolling up at the top. So mgh is the gravitational potential at the top of the hill, turns into linear kinetic and rotational kinetic. And then, because we can translate from rotational motion into linear motion, we can plug in, we can substitute, gotta annotate. We can substitute V over R in place of omega. So we can say 1/2 mv squared plus 1/2 times moment of inertia. I guess we're doing the solid one, 1/2 times 1/2 mr squared times omega squared, so v squared over r squared, because omega is v over r, so omega squared is v squared over r squared, equals mgh. Well, r cancels out, r squared cancels out, mass cancels out, and we get 1/2 v squared plus 1/2 times 1/2 v squared equals gh, which ultimately is 0.75 v squared equals gh. So we can solve for the final velocity if we wanted to. V equals the square root of gh divided by 0.75. We could figure out how fast, what the linear velocity of the solid cylinder is at the bottom of the ramp. And there's a problem like that on the practice exam, and so you will have a chance to look at that, and there will be a worked out solution for you. I don't like their algebra as much as mine because mass cancels out. It appears in every term, so why keep it around? Angular momentum. So remember momentum? Yes, that was fun stuff not so long ago. Momentum was P equals the product of mass times velocity. Angular momentum, L, is the product of angular mass times angular velocity. We did conservation of momentum. We have conservation of angular momentum. Clear? So conservation of angular momentum, when the figure skater kicks to start spinning, kicks the ice to start spinning, arms are out a little bit from the center of rotation, from the axis of rotation, so's that leg that kicked the ice. This skater is spinning relatively slowly. And then as they pull their arms in tight and their leg in close to the other leg, they spin faster and faster. We see that all the time on figure skating things. So this is conservation of angular momentum, that there's a certain amount of angular mass with a certain angular velocity. And then as they pull in mass tight to their rotation, then we have a case where the angular mass is decreasing. So if mass decreases, angular velocity has to increase in order to have conservation of angular momentum. Don't need to do the Earth. And that takes us to the end of the PowerPoint that we're talking about. But wait, I saw a better graphic for, so this one's just a little bit easier to see. The hoop moment of inertia equals mr squared. The solid cylinder is 1/2 mr squared, or mr squared over 2. Solid sphere is the bowling ball, 2/5 mr squared, and the hollow sphere is 2/3 mr squared. So just a few different ways of distributing the mass around an axis of rotation. Okay, that's the end of that. Let me get us back to the class. Give me one moment to find everything. Where did it go? All right. If you look at our page gonna go ahead and open up the key. Oh, I hate that. Oh, maybe it's fine. No, I don't like it still. I'm gonna open up the key to exam number 2, practice exam number 2, not the real exam yet. Unless it won't open for me. All right. So hopefully these things are here in a way that you can read them. Here's conservation of energy with rotational and translational motion. The practice exam will feature some questions that you've seen before from the homework or quizzes, some questions that you have not. I do not feel guilty if I take a question from the practice exam, particularly if it also appeared on the homework and or an earlier quiz, and then put it on the real exam. I will feel like I'm giving you fair warning on how to address the question. So here's this bowling ball. It's rolling and then it's going to go uphill. So it's conservation of angular momentum, linear, or conservation of linear kinetic energy, angular kinetic energy, and gravitational potential energy. At the bottom, it doesn't have any gravitational potential energy. It gains gravitational potential energy as it rolls up the hill. And in order to gain gravitational potential, it has to lose both linear kinetic and rotational kinetic energy. So as we follow the equations through, we call the bottom 0 and substitute, we wind up with, at the bottom, it's all linear kinetic energy and rotational kinetic energy. The rotational kinetic energy is 1/2 I omega squared, but here I've substituted in for moment of inertia, the 2/5 mr squared for the bowling ball, and for omega, V over R. So here we have V squared over R squared in order to substitute that in. So then we can cancel out the mass, we can cancel out the radius, and we wind up with a simplified equation, which still looks pretty horrifying, which is ultimately 1/2 V squared plus 1/2 times 2/5 V squared, initial, the bottom velocity, equals GH times 1/2 V squared plus 1/2 times 2/5 V squared up at the top. After that, it's just a lot of math, 1/2 times 2/5 to get a number to plug in there, 0.2, 0.5 plus 0.2 is 0.7. So we have these numbers that we can plug in and ultimately solve for the velocity at the top of the incline. A lot of math, but illustrating the concept of moment of inertia. A normal kind of momentum, conservation of momentum. Here's the cylinders rolling down an incline, and again, turning gravitational potential energy into linear kinetic energy. Conservation of momentum in 2 dimensions. Do spend some time on the practice exam working through these questions. I recommend opening up the practice exam, not the key, but just the regular practice exam, and seeing how much you can do without looking at the key for guidance, and then go to the key to get yourself past the other ones. If you do that, you should be pretty well prepared for exam number 2. All right. That, I think, is enough. So Friday is our last quiz of the semester, and it's on chapters 8 and 9 material. But it's a normal length quiz, so we will have time on Friday to field any questions you have before the quiz, and then you take the quiz. Then set aside some time to work on the chapter 10 homework and work through the practice exam so that we can productively use our time next Wednesday to make sure that you're feeling pretty good about that material for exam number 2 next Friday. All right, that is, I think, enough. Any other questions before we part ways? Okay. Have a happy Wednesday. I will see you on Friday.
Thank you,
Thank
Professor.
you.
Thank you.
Have a good day.
Professor.
Thank you.
Thank you, Professor. See you Friday. Have a great day.
Thank
you.
you.
Thank you so much for all your help.